Hello, everybody. Good evening. My name is Stephen Hummel. I'm our dark sky specialist for McDonald Observatory, University of Texas at Austin. And welcome to another live deep sky tour. We're going to show you some interesting, faint, fuzzy things out in the distant universe. We're going to be looking at some more galaxies tonight, continuing where we left off last week with our galaxy tour. But tonight we're also going to focus on a mysterious substance known as dark matter. I'll be talking more about that in a little bit. But I'm located under the dark skies of West Texas, and of course this footage is all red and grainy because I have to keep it dark in the dome for the telescope here behind me. And now we started this program at 9:30, but frankly that is a little bit too early. You can kind of tell that there's a little bit of a glow in the sky. This isn't a green screen, by the way. This is the real telescope here. It looks kind of fake in this video. But there is a little glow left in the sky, so the sun hasn't totally, disappeared just yet. So we're going to wait a few more minutes and we'll have a look at some interesting things. But thank you all again for joining us tonight. If you're tuning in, why don't you tell us where you're from in the comments section? I'm curious where all of you are from. So let us know if you're watching this live in the live chat where you guys are from. I'm just thrilled by all the different people who tune into these programs. But again, I'm located in far west Texas, and at McDonald Observatory out in the Davis Mountains of West Texas, here pictured in the daytime. But I'm located down at our visitor center in this little dome with the arrow at it with our 16-inch telescope. We're going to be using the telescope behind me to look at some galaxies and very, very distant things in the universe tonight. And if you have any questions for me or McDonald Observatory in general during this program, you are welcome to ask those questions in chat, and a team of moderators will be able to assist you. And then, if perhaps your question can't be answered in the short format of the text in the chat, or we think it's a good question, the moderators will send me your questions at the end of the program. So you're welcome to ask a question at any time. You don't have to wait to the end, but yeah, let the moderators know. Okay, so tonight we're going to be talking about a really mysterious side of the universe, and here explained in this little pie chart. So tonight we're going to be discussing in particular dark matter. And of everything in the universe, absolutely everything there is in the universe, the atoms and everything we know, everything you touch and feel, only makes up about 5%. Everything that's actually out there in the universe. The vast majority of the universe is completely unknown to us. It's made of stuff called dark matter and dark energy. And we can't actually touch or feel or interact with or see any of the dark matter or dark energy of the universe. It's completely invisible. So then how do we know it exists? Well, we can see the effects. Dark matter is something that's matter. It has mass, and it basically just sits there and gravitates. So it's got mass, which means it has effect on gravity, has a gravitational pull, and so if there's a lot of dark matter, things will be pulled into that area. So dark matter brings things together. Most of the universe is something else entirely called dark energy, and dark energy pushes things apart and accelerates the expansion of the universe, creating new space. So dark matter brings things together, dark energy pushes things apart, and everything else is just kind of along for the ride, and that everything else is everything we're made out of, and that's that little 4.9%. All right, but if we can't see or detect it in any way, then how do we know it's really there? Well, it's a really common question that astronomers get. How do you know all this stuff? Like, how do you know you're not just making it up? Well, the answer usually 9 times out of 10 is something called spectroscopy. Spectroscopy. And that's a big word, and someone who practices spectroscopy is called a spectroscopist. That's an even harder word to say. And this image here was taken from a spectrograph. And you've all seen a naturally occurring spectrograph before, a rainbow. So what a spectrograph does is it takes starlight and breaks it apart into its component colors, just like a rainbow does. But with a spectrograph, does it with more precision, and this is the result. So this is sunlight passed through a spectrograph to break it down into its component colors. And you got all the colors of the rainbow there. But notice the lines. Those gaps, those black lines are from elements within the sun absorbing that particular light. And each element on the periodic table absorbs a specific frequency of light. So a good spectroscopist can look at all these different lines and tell you the abundances of the elements in the sun based on that information. Because those elements absorb specific frequencies, which are always the same. So this is how we know what stars and other things, and galaxies and such, are made out of, by taking their light, passing it through a telescope, and breaking it apart with a spectrograph to get a result like this. But how do we know, say, dark matter is real? Well, we know that because even though it doesn't leave a direct result in the spectrum, dark matter can make things move around. And we can also measure motion with a spectrograph. Because if an object is moving away from you and emitting light, the light it emits is stretched out and it becomes more red. It's called a redshift. And if an object is moving towards you and emitting light, the light becomes more blue. It's blue shifted. Based on how much it's red or blue shifted, we can measure how fast it's moving towards or away from us. And the lines will be shifted in the bottom example over to the right if it's moving away. You can see the lines shifted to the right on the bottom. So this is the Doppler effect. You're probably familiar with this from the sound. Right, a car coming towards you is high pitched, and as it passes and moves away, it's low pitched. So we can measure how something is moving. All right, now let's put it all together. How do we know dark matter is a thing? Well, we know this by how galaxies move and rotate. Now, last time we looked at a bunch of different spiral galaxies, and we saw that they had that kind of spiral pattern based on how the stars move. Well, as it turns out, if you were to take a spectrum of a galaxy from the side that's rotating towards you, and compare it to the side that's moving away from you, you can measure how fast they're moving around. And when astronomers did this, notably Vera Rubin did this in the 1960s, what she found was that the galaxies rotate much faster than we expect. Galaxies are spinning so fast, in fact, that the outermost stars should be flung off into space if the stars and the gas we saw was all that there was there. What we predicted wasn't actually what we observed. And what we observed could only exist if something were there, some invisible form of matter were there within the galaxy that is keeping it together. And to elaborate on this, if we measure the rotation of a galaxy at the center, we see it spinning around at a certain speed. But the further away you get from the center, the further on the right on the graph you go, we expect the stars to be orbiting more slowly. But instead, they orbit faster. And that can only happen if there is this substance known as dark matter keeping it together, allowing the galaxies to spin around that fast and keeping it in its nice spiral shape. So that basically was some of the first proof that dark matter has to be a thing. We don't know what it is. We can't see or touch it or any way, but it has to be there. So we're going to take a look at some galaxies tonight. And we're going to keep that in mind. And we're going to come even later and look at some entirely different approach to show that dark matter must exist with our very last object. But we're going to look at some galaxies, and I kind of want you to keep what I just said in mind, how we can measure how it's spinning, how we can measure that it's spinning so fast that it should fly apart if it weren't for something clumping it together. All right, but our first galaxy we're going to look at is known as M82, or the Cigar Galaxy, and it's a relatively bright galaxy in the sky. And if you'll give me a quick second, we're gonna pull up a view now that it's well and truly dark. Now you can notice the glow behind me is gone. But the Cigar Galaxy M82 is located in the northern part of the sky, and it's kind of in the constellation of Ursa Major, the Big Dipper. So we're kind of looking north. So that's north there now. And again, you can ignore this band. This is the middle point of the sky. But the Cigar Galaxy is nicknamed that because it's kind of lumpy and, cigar shaped. All right, but there's our live view of M82, the Cigar Galaxy. And M82 is pretty different from most of the galaxies we've seen so far in our previous live tours. For a long time, astronomers classified this galaxy as an irregular galaxy, meaning is kind of just a lumpy mess that didn't really have much obvious structure. But now we know that it actually does have, here, I'm going to reset the exposure there. It actually does have a spiral structure within it that isn't visible to us. But here, I'm improving our view there. There we go. But we can't see it because it's roughly edge on. Again, this galaxy, like any galaxy, is going to be spinning. And let's say this side is spinning towards us, this side is spinning away. That means that the light we see from here, pass through the spectrograph, if it's spinning towards us, would be slightly more blue, and the light we see on the other side would be slightly more red. And that's how we can measure how fast the galaxy is spinning. All right, but if we were to look at our chart of different galaxies from last time, we've got our Hubble divocolors diagram here, classifying the many different kinds of galaxies that there are. For a long time, astronomers thought it was an irregular, so way on the very far right. Now we know it does have kind of a spiral structure to it, but it's just not very obvious. So it's kind of somewhere in the intermediate spirals to irregulars category. And we think that it probably got so disformed because of a presence of another larger galaxy nearby we saw on our very first live stream, M81, the first galaxy we looked at back in early April. And on that galaxy, we saw nice big spiral arms, but it's likely that this galaxy and that other one interacted in the past, and that kind of made this one get all jumbled up, essentially. We've got another satellite here on the left. And essentially that jumbling up, that mixing up of gas, has caused a burst of star formation in this galaxy. This is, in fact, one of the most common examples of a starburst galaxy that you can see in the sky. It's forming new stars at an incredible rate. And if we look at a deeper exposure taken previously here, let me get that up for you here. We can see that this much deeper, several-hour exposure that it's got these red plumes streaming off of it. And this is hot gas. It's actually being blown off from the heat and energy of lots of stars forming and dying very quickly, as well as other activity within the core of the galaxy. Sorry, that's M82, the Cigar Galaxy. Very lumpy, irregular, kind of oddball galaxy, but actually very bright. I chose to look at this one first because even though the sky isn't 100% dark, it actually still shows up. It's several times brighter than our Milky Way, even though it's much smaller. So it's also 12 million light years away. So it's the closest galaxy we're going to look at tonight. 12 million years for the light from this galaxy to reach us. Okay, but we've got a lot more interesting galaxies to take a look at tonight. And the next one we're going to have a look at tonight is known as M64, or the Black Eye Galaxy. Black Eye. And that's a really good name for it because it really looks like that. But it is located over right now, kind of high in the east and It is near the constellation of Virgo. It's actually in another constellation called Coma Berenices. All right, and you can see the telescope moving behind me. I'm going to start moving the dome as well. All right, and I'm going to turn the lights off in here so we get it nice and dark. Don't want that light spoiling our view. It helps to see the telescope, but it does kind of interfere with the telescope's view just a little bit. All right, so that's where we are in the sky. And give me a quick moment, and we will start seeing the Black Eye Galaxy M64. Alrighty. Okay, so just a quick moment to get it all centered up for you here. All right, so this galaxy is 17 million light years away, and here, it's going to take the picture here in just a second. There it goes. And you can see that it's got a kind of a disk, a stars surrounding it, a kind of halo, and then a darker line in the middle there. The view will slowly improve as we watch here. It's going to start getting a lot better than that, a lot less grainy pretty soon. But this galaxy is an example of a flocculent galaxy. Flocculent. And flocculent is literally just a fancy term for fluffy. It's a fluffy galaxy. That's really all it means. And when astronomers say a galaxy is fluffy, when astronomers say a galaxy is flocculent, what they really mean is that the spiral arms are wound very tightly. So you can see that there's this smooth outer area to the galaxy, but the area in the middle has got these lines of dust, actually. That's what that is. That's why it's dark. It's dusty there. But if you were to like try to count the spiral arms there, you're going to have a hard time. They all just sort of blend together. So it's very, very tightly wound. And as we expose longer, the more details will come into view. But I mentioned earlier the astronomer Vera Rubin. Vera Rubin's a very famous astronomer. She was widely credited with not the first, but very early evidence for the existence of dark matter. And she took observations of galaxies and looking at how they were spinning, right, and noticed that they were spinning too fast. Then astronomers found this galaxy, and they said, wait a minute, something's not right here. Because the stars and dust in this galaxy aren't all going around in the same direction. The outer area, they're going around one direction, but in the inner core, the gas is going around anti-clockwise. It's going around the other way. But even though the gas is going around the other way, the stars are moving around. And that's very strange. And Vera Rubin took a look at this, and she realized that the only way that this could happen is if the galaxies merge together. And essentially, why it's spinning in opposite directions is because of basically a leftover rotation from a previous galaxy which has merged with this one. And that actually was quite surprising at the time in the 80s and 90s because astronomers thought that spiral galaxies didn't merge. But then again, this isn't your typical spiral galaxy because although it's very clumped together in the center, notice how blank the outer area is. It's very smooth. And so it's kind of a sign that there's not really a lot of star formation going on there. So the galaxy we looked at before that was M. I'm sorry, M82. And M82 is forming lots of new stars at a tremendous rate. This one, it's not really. It's kind of a much slower pace. It's probably consumed all of the gas it has to form new stars in the outer regions, which is why they're so blank and devoid of detail. But there's still some gas in the center. So it could still be forming some stars in that region. All right, so the Black Eye Galaxy. Vera Rubin suggested that this galaxy be renamed to the Sleeping Beauty Galaxy, and that's a nice, pretty name. I don't really see it. Personally, I think the Black Eye Galaxy is just a really good name. It really suits it well. It's got that, looks kind of like a droopy eye. All right, so in our diagram here, this galaxy is an unbarred, and it's kind of in the SA category. So it's kind of a between lenticular and spiral. So it's kind of got elements of both going on in it, kind of a hybrid in a way. Let's have a look at a longer color exposure there, and you can see that even in a much longer color picture, the outer regions don't have a lot of action going on, but the center does. There's still some star formation in the center from all that dust. And you can see how tightly wound the spirals are in there. Again, the flocculent galaxy. All right, so I like this galaxy a lot. It's a pretty good one in an amateur telescope as well. It's reasonably bright, and you can kind of see that part in the center. Alrighty, so up next, we've got another very interesting galaxy. And this next galaxy is M61. And M61 has been in the news a little bit lately because it's got some action going on inside of it. And I'm going to slew the telescope over to it. Not going too far to get to it. We are located kind of in the Virgo cluster, which we looked at last time. Some other galaxies in the Virgo cluster. You can see there's a whole bunch of galaxies. Every one of those little red dots is a galaxy in the Virgo supercluster, for the most part, in that clump near where my little laser pointer is pointed. And this one is no exception. Alrighty, so let me set the exposure up for you here. It'll just be a minute. But M61 is a nice spiral galaxy, kind of well, it's sort of in the middle. It's an intermediate spiral galaxy, and it's kind of made the news because it's got a nice bright supernova going on inside of it. So there it is. It would look a little slightly worse than this in an amateur telescope. This is kind of maybe in a very nice telescope it would look like this. It is a relatively faint galaxy. But if we take a look at there's some other galaxies in the area here, but we're looking particularly at the biggest one here. That's M61. And you can see that it's got a very bright core, kind of panning up here. And then it's got these two dots. One of these is a star, and one of these is actually an exploding star within the M61, the swelling spiral galaxy. So I believe it's this one actually. This is a supernova, which means it is a star within that galaxy, not in our own, that is 52 million light years away, that has exploded. And this was a relatively massive star that ran out of fuel, and when it ran out of fuel, essentially in just a few moments, it collapsed down on itself, and as it compressed down on itself, it suddenly heated up at the core enough to restart nuclear fusion, and then it detonated all in one tremendous moment. And I have a simulation of that, a computer simulation of that moment. And it is right here. I love this. It's got a little music to it as well, which I just think is super cool. So this simulation is only the first 150 milliseconds after the star detonated. The colors here represent the temperatures. So greener is colder, while in a moment we'll see the colors turn yellow and red, meaning hotter temperatures. You can notice it starts out very symmetrical, but then it quickly devolves into a lumpy mess. So supernova explosions are cataclysmic events. Again, this is only the first 150 milliseconds of that explosion. And all that gas and heat as it expands off, eventually, that debris will expand away and it could even be recycled and be part of new stars. Lots of elements heavier than iron are generated in this moment. This one fleeting moment in the whole span of the universe can be responsible for some incredible things many millions of years later on. So we really owe supernova explosions like the one we're witnessing right now for essentially life as we know it. Every element heavier than iron, for the most part, was likely generated in a very massive star exploding all at once. And what makes this one so interesting is that it's relatively bright, and it is possible to actually see it with an amateur telescope. We looked at an example last week, which is a similar kind of thing, but it was fading. This one was discovered on May 6th, and it is actively getting brighter just a little bit. And this is probably around peak brightness right around now. And then over the next few days or weeks, it'll slowly fade away until it's basically gone, and we'll have to wait for another one. The good news is that this galaxy is currently near the top of the leaderboard for most supernovae going on within, like a human lifetime. I think we've got 8 or so far in the past 60 years. That's a lot. Now, galaxies contain billions of stars, but most of the time that only the very massive ones explode, and they still live millions of years. So to have a more than one supernova in 10 years is really an incredibly fast rate that the stars are dying off. And it's a sign that this galaxy is forming a lot of new stars, and they're forming very massive stars, which are then dying. So it's very possible that this galaxy will actually blow itself apart in enough time. All those explosions heating up the surrounding areas will heat it up so much that new stars can't even form anymore. It's very likely that that's kind of the fate of this galaxy. A lot of star formation now, but it can't keep that rate up forever. Here's a color image taken by the European Southern Observatory's very large telescope, and you can see lots of pinks and blues in there, and that's another good sign that there's a lot of star formation going on within this galaxy. So again, that's M61. M61 on our chart is an SAB little b, so middle row, intermediate, second on the middle row. It's kind of in the middle in every regard, but it is very very active galaxy, more so than almost any other within our local universe, at least. All right, so now let's take a look at the exact opposite. We just saw a very active galaxy. Now let's take a look at a pretty but not nearly as active kind of galaxy called a lenticular galaxy. And on our map, let's go back to our map. This next galaxy is known as NGC 4762, and it's also known as the Paper Kite Galaxy. I haven't actually seen a lot of people use that name, but well, I saw one person using that name, and I liked it, so I'm going to go with that. The Paper Kite Galaxy. Let me see if I even have to move the dome, because I didn't even have to move the telescope very far there. Now, it's a tiny dome movement. Alrighty. And we should be on target here in just a quick moment. Yes, there we go. All right. Look at that. Didn't have to center it at all. All right, so we've got a very thin edge on Galaxy. Okay, so we've got an edge on Galaxy. So if we looked at the previous galaxy was face on, which means it's very hard to get an idea of how fast it's rotating because it's not moving towards or away from you. So that redshift trick doesn't really work. But it would work very well for this galaxy because as it spins, one side is moving towards and one side's moving away. We can see the red and blue corresponding shift for the galaxy with a spectrograph. Zooming out, we can see that there's another galaxy over here on the right. This is NGC 4754. It does not have a nickname, but both of these are the same kind of a galaxy. They are both lenticular galaxies. And so if we look at our chart again, we can see that lenticulars are kind of in between the intermediate spirals here and the ellipticals on the left. So most lenticulars, lenticular really just means shaped like a lentil in a way is how I remember it. Um, they're very smooth and they don't have a lot of structure. But lenticulars are generally kind of retired galaxies. That they were once spirals, probably, but they don't have that spiral structure anymore, and they're not forming any new stars. So they are just basically uh, retired galaxies. They still have stars in them, but they're not actively forming many more. So sometimes galaxies call, or sometimes astronomers call galaxies like this quenched, meaning they've basically, for whatever reason, stopped being able to form new stars, like someone threw a wet blanket on the fire, so to speak. And this galaxy has a very active, bright center because it has most likely either a massive black hole in the middle with stuff falling in, heating material, and causing it to glow. That's probably what's going on. You can also begin to see that there are these kind of streams coming off of this one. And that's a sign that this galaxy likely many millions or billions of years ago merged with another galaxy. And that merger event got the stars kind of all kicked out of orbit. And so some of them are still kind of hanging out further away from that merger event, likely billions of years ago. It looks like the galaxy on the bottom is close, but it's actually not. This one is 58 million light years away, and this one is 53 million light years away. So they're actually 5 million light years apart, and the smaller one is in fact closer than the bigger one. It just goes to show that size is kind of not always the most accurate way to gauge the distance. It could be smaller and closer, or not. You have to develop other methods of determining distance. You can't just always rely on that. All right, so really like this galaxy. This was also on the thumbnail for this event, but here's the picture again, and you can see even in a color picture, and mirror flipped here, that neither galaxy has all that much color, especially compared to the ones we looked at before, and that's a classic sign that it's not forming new stars and that they are essentially basically retired now. They've been quenched. I think I've never actually seen any other galaxy that's so perfectly colorless as 4762 on the lower right. Again, the paper Kite Galaxy. So I find that rather a curious fact about it. All right, so with every target we've looked at so far, we've been looking further and further away. The first thing was 12 million light years, then 17 million, now we're in the 50s to 60 million light year range. The next target we're going to look at is incredibly unimpressive visually. Of everything we've looked at so far in this program, they've been relatively, photogenic objects. But the next thing we're going to look at, it isn't going to look like all that much. But I want you to bear with me because in reality, what it is easily the most impressive thing we've seen in this program, and I think maybe we'll ever see in a live stream format like this. And it's known as the twin quasar. And the first thing you should know about it is that the twin quasar is 8.7 billion, with a B, light years away. Everything else we looked at was in the millions. Last week we looked at the Coma cluster, which was 330 million. The next object we're going to look at is 8.7 billion light years away, and it's up there for the most distant thing you can possibly see with an amateur telescope. Let me come back. Didn't mean to actually put that up there. So let's take a look at our map here, and we're going to go back to the constellation of Ursa Major. So we're kind of looking in the north. Whoop, sorry about that. Let me fix that here. There we go. So that's where we're going to go. All right, and I'm going to start moving the dome. Turn the lights on a little bit so you can see it moving around. Almost there. Just a little bit further. There we are. All right. So now we should be relatively close to being on target. Okie dokie. Now remember, first, it ain't gonna look like a whole lot. But yet we got it right in the center. Okay, so do you think you see what we're actually trying to see? Probably not, because at first it just looks like a whole bunch of stars. But these two things here in the center, those are not stars, those are quasars. Actually, the same quasar twice. It's the twin quasar. All right, so what's a quasar? Well, a quasar is basically a portmanteau of quasi-stellar object. It looks like a star, even though it's not. Sorry, I keep having an issue with my microphone where it keeps disconnecting. But yeah, quasi-stellar object. Keyword quasi. It's not actually. So what this really is an enormous object that is basically a galaxy 8.7 billion light years away. And at the heart of that galaxy is a supermassive black hole, a true monster of a black hole, and a ring of dust and gas falling into it. And as the stuff falls in, it gets incredibly hot, millions upon millions of degrees, just unbelievable conditions, an immediate area around that black hole. And right before it falls in, material, as it's heated up to incredible temperatures, is then pushed out perpendicular in a jet, coming out away from that supermassive black hole. And so anytime something falls in, we see the quasar getting a little bit brighter. And so they can actually change a little bit in brightness. That's one clue that it's not a true star, is they kind of pulsate a little bit sometimes. They also emit a lot of radio waves. And that's how some of these things were first discovered, was from their radio emissions. And normal stars just don't do that. But what makes this particular quasar so special, not just because it's a massive black hole, probably billions of times the mass of the sun sucking things up, 8.7 billion light years away, if that enough isn't impressive for you, we're seeing the same thing twice. We're seeing the same quasar's image twice. And here's the real weird thing about this. If something falls into that black hole and it gets a little bit brighter, we see a little more emission. We see this one get a little bit. We see this one get a little bit brighter, right here. And 14 months later, we see the same exact thing happening to the one on top. Something happens here, exactly the same thing happens 14 months later there. What in the world is going on? Well, it's probably some of the best evidence for dark matter. It's known as gravitational lensing. And here is a Hubble Space Telescope image of the region we're looking at right now. So it's the same thing we just saw, but a very deep exposure, many, many hours of exposure with the Hubble Space Telescope, right? So we're probably never going to get a deeper image than this. And you can see that there's a big elliptical galaxy, right? Ellipticals meaning they're big, kind of egg-shaped. And that elliptical galaxy's got a lot of mass, but it's also got a lot of dark matter around it. And what we're seeing, you see those two bright points on top and just to the side of it? That's the 2 points we just saw in the live view. So what's going on is something called gravitational lensing. And here's an animation of how this works. The light is being emitted, but then there's a lot of mass. And the bigger something is, the more massive it is, the more it will distort space and time. And light may not have mass, but it's traveling through that space. And because the space itself is warped, it gets lensed and bent and distorted. Now, it's going to repeat that so you see again. So the quasar is 8 billion light years away. The light happens to pass right by this massive elliptical galaxy filled with dark matter as well. That's how it's so massive. And because space and time has been bent, we're seeing the same object distorted twice. And the reason one takes longer to reach us, the brighter one reaches us first, and then the one on top reaches us later, is because the paths they take aren't the same length. One's lensed a little more than the other. And so one has a more direct route compared to the other one. So once again, this is a lot of concepts going on. Just to recap, there's a supermassive black hole 8.7 billion light years away. Matter's falling into it. It's heating up and it's emitting this jet straight out for reasons we don't even quite understand, but it may have something to do with an intense magnetic field around that supermassive black hole. That jet is aimed almost squarely at us. The line that the light takes happened to pass through this massive galaxy with a lot of dark matter to bend space and time so that the light is split off a little bit, or is actually bent towards us, following curved space and time to reach us. And because of relativistic effects, when a quasar is aimed straight at us, it actually appears even brighter. And that's how we're able to see the same object twice in two different locations. And it's that bright that you can actually see that in an amateur telescope, even though it's 8.7 billion light years away. Well, if that doesn't impress you, then frankly, I'm not really sure what would. I think that's one of the most impressive things that is even remotely possible to see in an amateur telescope. So let's just look at it one more time. We've got one on the top, one on the bottom, and that's kind of what it would look like with an amateur telescope, a very serious one. This is not an easy object to find. You need a pretty large telescope with a lot of magnification to do it, but you can do it with an amateur telescope. And I'm pretty sure it's the most distant thing you can see in an amateur telescope. So just to let that sink in even more, 8.7 billion years to reach us. The Earth is only about 4.5 billion years old. So the light we're seeing is almost twice as old as the Earth itself. And the universe itself is 13.8 billion years old. So it took the bulk of the age of the universe itself for the light to reach us. So that quasar almost certainly doesn't exist anymore. And in fact, we find lots of quasars out at that distance. In the earlier stages of the universe, quasars were more common than they are now because it takes a lot of power to get those things going, and eventually it burns through. Essentially, all that matter either falls in, it gets quiet. So we don't see them quite as often in closer to us. We have active black holes, but not quite as active as this true monster was that many years ago. All right, so I think that's probably gonna be the forever the most distant thing we look at in this in this live kind of program. I can't think of anything else that is that far away that we could possibly see. And even things just a few billion light years away is very tough. By the way, that was the first known confirmed example of gravitational lensing. It was discovered in the 1970s, and it was quite a stir at the time. So yeah, if you have an amateur telescope, it's a challenge, but you can in fact see it. All right, so that's where I'm going to wrap up our live viewing session. I think uh, going to start taking some questions soon. If the moderators are going to start sending me questions my way. Um, Alrighty, I've got quite a few lined up here. Okay. Anna Rader asks, why do galaxies have different colors? Well, the color is often a sign, essentially, of what's going on. The red colors you often see, speckles of red, are from very massive stars heating up hydrogen around them, and the hydrogen glows a particular red color. Blue in a galaxy is usually also a sign of a lot of large hot stars. The hotter the star, the more blue it shines. Uh, Redder or whiter galaxies only usually have smaller, lower mass stars that don't shine as brightly. So yeah, the color can tell you a little bit about the general health and status of a galaxy. If it's got lots of pinks and blues, it's lots of big stars. If it's more red or pale, then it's probably not forming a lot of new stars. Okay, Jack Horkampare. I hope I'm pronouncing that right, Jack Horkampare. You average stacking images to smooth out the random noise. Yeah, I'm stacking the images together so that the noise hopefully will be averaged out. Speaking of noise, I know that my video is a little noisy right now. I'm going to turn the lights back on for you. There we go. That's a little better, so you can see me again. All right. Anna Marie Beckmeyer asks, why are there so many galaxies clustered in Virgo compared to the rest of the sky? So the Virgo cluster is our local supercluster of galaxies. And when we look at the grand scale structure of the universe, what we see are lots of clusters of galaxies. And I do have, I believe, yes, a map of that. So yeah, the Virgo cluster, supercluster, is located here in the center in this map. But looking out hundreds of millions of light years in any direction, we see lots of other similar clusters with lots of galaxies. And generally speaking, gravity and especially dark matter acts to bring these clumps of galaxies together and keep them there. All the mass of galaxies essentially has a snowball effect. If you start to get a clump here, you're going to get make kind of try to keep it bigger and bigger and bigger. So they'll tend to fall together into clumps. But that's not always going to be the case due to the expansion of the universe. The galaxies eventually will be pulled apart from each other, and gravity won't be enough anymore. And we'll talk about that more next time. Okay. Okay. Jennifer Jackson asks, why isn't all the light we see emitted by stars, galaxies, and space objects bent like the light of the quasar? Well, technically speaking, it is. It's just not enough for it to be noticeable. But even the sun can have gravitational lensing. In fact, if you know this, you can't look directly at the sun, but during an eclipse you can. And in fact, that's how Einstein's theory of general relativity, the first evidence for it, was by seeing how the sun's immense gravity bent space and time so that stars appeared in different places. It always is. It just takes a lot of mass really clump together, which especially happens if there's a lot of dark matter in an area. For it to be particularly noticeable. And there just isn't usually enough massive objects in front of a light emitting object behind it for the effect to be all that common noticeable. But technically speaking, it is actually happening. It's just our eyes can't usually tell. Alrighty, let's see some other questions here. Um, okay. Lindsay Minton asks, how does a quasar form? That's a good question. And we think basically you get a lot of mass together really relatively quickly, meaning you have to have a supermassive black hole, and you have to have a fresh supply of gas and stars and stuff falling near it. Not necessarily into it, but they gotta be in the neighborhood to be sucked in. And so we think that happened more often in the early universe when galaxies in general were closer together before the universe expanded more as it is now and things got a little further apart. And so maybe earlier galaxies had an easier time accumulating that much stuff. And oftentimes you can have what we call an active galactic nucleus, and that's when you have a black hole swallowing a lot of matter, but it's just not enough to get it incredibly hot for those jets and such to form. So it's got to be a really big black hole, and it's got to be a lot of stuff following in. And oftentimes those conditions don't last for that long in the grand scheme of things. Okay. Ted Betters asked, how do I stack exposures? I am using a program called SharpCap, which stacks it for me. It finds the stars, it lines them up, and then it combines them together. It's a live stacking feature in SharpCap. What is the best bet about dark matter? Asks Daniel Roy. Is it neutrinos? I don't know. No one really knows what dark matter is, right? That's why it's kind of so interesting. I honestly don't know anymore. I don't think any of the ideas out there right now are sufficient. But there are a lot of ideas, I should say, and frankly, they just can't all be true. There's a lot of them disagree with each other, and I'm not even going to weigh in because all bets are off. I don't think any professional astronomers really know what dark matter really is. Um, yeah, if I knew, I'd have a Nobel Prize, that's for sure. Ramesh Babu Nagarajan asks, is the M61 supernova is going to end with a neutron star or black hole? Is that known? We don't know how it's going to end. It can be hard to tell. Um, we're not really sure what the ultimate fate of that star is. It was only discovered on May 6th, so there hasn't really been enough time for us to gather any more data on what the fate is. It could be either one. It could be a neutron star. It could be a small black hole. Both are possibilities, but too soon to say. Um, Anna Rader asks, this will be my last question here. Here's a weird question. This is her words, not mine. Are there any weird theories out there about the bending of space-time, black holes, space travel, or time travel? Well, uh, so in terms of like bending space and time to for space travel or time travel, um, well, time travel is real in a sense, but it only goes one way. You can only go forward at a slower rate due to the effects of general relativity. I think that's pretty weird. That's real. I mean, like satellites in orbit around Earth, they experience time at a slower rate because of their speed than we do here on the ground. And that's not like a theory. That's literally happening. And if the satellites didn't account for that and their atomic clocks, then GPS wouldn't work. I think that's just fascinating. That these very abstract concepts have very real world implications. Um, in terms of like trying to travel through space, I think it's interesting to think about. I don't really see us bending space and time to travel through space within our lifetimes. That's at least. I'm not really sure uh, how you would go about doing that in a way that a human could survive the event of traveling. You can. There are some ideas out there for engines and such that bend space and time, basically to propel the craft forward at faster than light speeds. But there's no real plan on how to actually create that, or no way to create enough energy to get that process started. Um, So there's interesting brain food out there, lots of interesting things to think about. But in terms of space travel, I don't think we're going to see that in our lifetimes. I wish it'd be cool. I hope I'm wrong, but I'm not too optimistic about that. Okie dokie. Well, that's going to wrap up our live Deep Sky program. And next time, we're going to talk a little bit more about the expansion of the universe and look at some other pretty galaxies. And tune in next time for that. That'll probably be next week, most likely. And you can subscribe to this channel or follow us on social media, and we will post about the dates for future programs. I thank you all so much for joining me. This has been a pleasure. I always love looking up at the sky with y'all. And clear skies, y'all. Keep looking up.